The transformer architecture set the standard for natural language processing, organizing massive streams of text into coherent understanding. But for years, computer vision remained the strict domain of convolutional neural networks. The reason comes down to a core bottleneck in the standard transformer block: self-attention. Self-attention requires every single token in a sequence to look at every other token to calculate its relevance. If you treat every pixel as a token, the math breaks down. The network connects every pixel to every other pixel, exploding the cost. This scales quadratically. Due to this O(n)² complexity, running pixel-level attention requires more compute than any system can handle. The Vision Transformer paper proposes a remarkably simple bypass to this bottleneck. An image is worth 16 by 16 words. Instead of feeding the model pixels, ViT explicitly treats an image as a sequence of words. It maps visual data into the format required by a standard text transformer. To see how this works, we need to trace the data flow. First, the front-end tokenization, the standard encoder pass, the impact of massive data, and the internal spatial structures. Solving this initial tokenization bottleneck allowed researchers to use a single, unified architectural design to process both human language and visual reality. This 3D block represents a standard 2D image matrix. The first step is cutting this image into a grid of non-overlapping patches. Each patch is flattened from a 2D square into a 1D vector and passed through a linear projection, compressing it into a standardized dimensional embedding. Mathematically, this projection step is exactly equivalent to running a 1D convolution where the kernel size and the stride both equal the patch size. Next, a specific class token is prepended to the sequence. This is a structural heritage borrowed directly from the BERT model in NLP. The model updates this class token as it moves through the network, and its final state is what the model will ultimately use to make its classification. At this stage, there is a vulnerability. The tokens exist as an unordered sequence. The model has no way to know which patch came from the top left versus the bottom right. The solution is to add learned one-dimensional position embeddings to every token, establishing their exact order. The architectural novelty of ViT exists almost entirely in this front-end preparation. By turning patches into standard embeddings, it dissolves the barrier between spatial pixel data and sequential token processing. Once the image is tokenized, it enters a standard Vaswani transformer encoder block. There are 0 vision-specific modifications inside this component. This block uses the internal components you find in text models: pre-layer norm, multi-head self-attention, MLPs, and residual connections. Because the encoder is standard, it remains governed by the O(n)² self-attention constraints we established earlier. This introduces the primary architectural lever of the ViT model, the patch size. Sequence length equals total image resolution divided by patch size squared. This creates a direct trade-off. Large patches yield a shorter sequence, which is computationally cheap but coarse. If you attempt to increase resolution by halving the patch size from 16 to 8, the total sequence length quadruples. And because attention costs scale quadratically, quadrupling that sequence length squares the computational cost of the attention mechanism. Patch size, rather than layer depth or model width, operates as the primary lever trading spatial fineness against raw computational expense. Structurally, ViT operates with near-zero vision inductive bias. To make this architecture work, it requires immense data scale. Inductive bias is the set of assumptions baked into a model. CNNs use convolutions to bake in human priors, like local neighborhood grouping and translation equivariance, directly into their math. ViT strips those assumptions away. Its self-attention mechanism is global across all tokens from step 1, and only its MLPs maintain any local constraints. This chart highlights the immediate drawback. When tested on standard, relatively small datasets like ImageNet, ViT overfits and crashes below standard ResNets. Without the training wheels of convolutional bias, ViT lacks the inherent structure needed to learn spatial rules from a limited number of examples. Specifically, researchers utilized the internal Google JFT dataset containing 300 million images. When we expand the axis to pre-training on 300 million images, the performance dynamic flips entirely. Given enough data, ViT manages to beat state-of-the-art CNNs on downstream tasks, and it does so while requiring 2 to 4 times less compute. At sufficient scale, A generalized architecture fed massive data will outperform an architecture constrained by human-engineered biases. This raises a critical engineering question. If ViT is essentially blind to 2D space and has no built-in spatial biases, what do the model weights actually learn during that massive pre-training phase? To find out, researchers analyzed the one-dimensional position embeddings after training to see how they had organized themselves. This visualization shows the result. The 1D vectors self-organized into a perfect 2D topological grid. Patches physically closer to each other in the original image learned highly similar embeddings, despite the model never being explicitly told they were neighbors. The researchers then analyzed the attention heads, tracking how the attention distance changes as data moves deeper into the network. In this scatter plot, we can see that in the early layers, heads attend very locally. Then, in the deeper layers, the attention heads spread out to process global context across the entire image. ViT did not discard the local-to-global hierarchy of CNNs. Rather, it rediscovered that exact hierarchy from the data alone, proving human-engineered spatial bias is unnecessary. At publication, the architecture had limitations. Self-supervised masked training lagged behind supervised learning by 4%. The model only handled classification, and replicating the results required the private JFT300M dataset. Despite these initial limits, ViT definitively proved that a single, unified transformer architecture could process both text and images natively. The concept of treating an image as a token sequence laid the direct groundwork for modern multimodal vision language models and systems like CLIP. ViT's patch token sequence also defines the compressed latent space used by latent diffusion models to generate art. There are 3 main takeaways. First, an image is processed by slicing it into patches, flattening and projecting them into standard tokens. Second, patch size is the sole architectural cost knob, trading spatial fineness against an exponentially exploding attention cost. Third, at a small scale, inductive bias wins, but on massive datasets, generalized architectures dominate. The vision transformer proved that the key to artificial intelligence isn't forcing models to see like humans. It's giving them the raw data to learn how to see for themselves.